you all for coming, and I'm so excited about this fabulous fest. Never seen so much, such a broad coverage of so many deep topics. So we're going to have a good time here. So I'm going to talk about parallel algorithms for matching, and this is work with Nima Nari. I just want to say a word about matching. It occupies a very distinguished place in the theory of algorithms. And it has given rise to some of our most central notions in the theory of algorithms. So Jack Edmonds defined polynomial time, Les Valiant defined sharp p-completeness, and in this work with Jerem and Valiant, we gave a polynomial equivalence between random generation and approximate counting for self-reducible problems, and that sits at the core of the MCMC method. So these are all bread and butter issues for all of us, but matching has shown us the way, even in slightly more esoteric, still mainstream models of computation. So I hope this comes and goes, right? But okay, it goes. It comes. Okay. So Rasborov, for instance, in the 80s, showed us how to get a super polynomial lower bound on the size of monotone circuits while working on perfect matchings. And in the 80s, also, Yanakakis gave this notion of extension complexity of a problem and conjectured that it should be exponential for TSP polytope. And Rothwas first gave an exponential bound for matching and then extended that for TSP, giving the first bound for exponential bound for TSP. So many more. I mean, this is by far a short list. It plays a central role also in game theory and economics. And these days, matching markets have become a big thing. And Gail Shepley introduced stable matching, which started this field. It's a Nobel Prize work. Changed our lives in many ways. Think of the AdWords market. Then Shepley-Shubik completely characterized the core of a two-sided transferable utility market by using bipartite matching, the LP for bipartite matching. And with the matching markets going into your iPhones, online bipartite matching became very important, and this work led to, I don't know, 50, 100 different generalizations, so on, for these kinds of markets. So, I mean, this is by far a small list. So, everybody knows what a perfect matching is. It's a subset of the edges of the graph such that each vertex has one edge incident at it. And here are two fundamental computational problems. The decision problem is there a perfect matching in the given graph? And the search problem is to find a perfect matching if one exists. And we're talking about parallel algorithms. So these are maximally parallel algorithms. So NC is the class, very fundamental. It captures beautiful problems solved in a most fantastic way. I mean, in a very fundamental way, using fundamental properties. Here, each processor can only work for polylog time, which is so short that it cannot even read the entire input. Okay, but then you have a polynomial number of processors that are sharing a common memory and can therefore compute something big about the whole input. And NC is the deterministic class. RNC is where you have randomization. And as you can imagine, one of the main issues here is how to make these processors think about the same thing, right? Sometimes randomization has played a key role in that, and I'll show you how. In '79, Lowas wrote a fantastic paper on matching, for the first time, he showed us how to find matchings using not combinatorial means like Edmonds, but using linear algebra and randomization. And he didn't talk about parallel algorithms in this paper, but it was clear that it could solve, his methods could solve the decision problem in RNC. But the search problem was still open, and then Karp, Opful, and Wigderson gave the first algorithm. And it was followed by our work giving a slightly simpler algorithm, but the more important thing is that it gave rise to the isolation lemma, which I think is the main contribution from the parallel perspective to the rest of the theory of algorithms and complexity theory. It's been found many, many uses. And I'll tell you what it is about. So at this point, we're still using randomization. It's not the end of the game. We should do it deterministically. And that became an open problem, big open problem, more than 30 years old. And it's sometimes called the Mount Everest of theory. And it is just as useless as going up Mount Everest. Because nobody's going to ever use an algorithm like that. And people often ask me, why do you work on it for so many years? And I say, because it is there. Yeah. But putting these jokes apart, I think whoever gets there first would have given us something for the rest of the field, my guess. Okay, so in the last 5 years, there's been tremendous progress on this problem. First, for the bipartite case, okay, so people came up with these two absolutely fabulous relaxations of NC. So NC is very difficult, so they said, okay, let's relax NC. So quasi-NC is where you have not polynomially many processors, but 2 to the log n polylog n processors. So super polynomials are exponential number of processors. And these two works solve the general and the bipartite and the general graph case, and many, many new ideas came about here. And then your own Shafi Goldwasser with her student Grossman gave what's called they defined this notion of a pseudo-deterministic RNC algorithm. They did it for bipartite graphs. What is this? It is like a deterministic algorithm, but it uses randomization. Okay, so if you run it over and over again on the same graph, it'll almost always give you the same perfect matching. Okay, so with very high probability, it gives you the same solution. In that sense, it's like a deterministic algorithm, but use lots of random bits. So it seems like magical, but I'll show you how it's done a little bit. Okay, so our work started by trying to extend this to general graphs. Okay, and but before I can even state our results, I have to show you some key ideas from the MVV work. And okay, so our viewpoint was the following. The main difficulty is how to make all these processors, which cannot even look at the whole input, think about one matching out of, however many matchings there are, 1, 2, 15, polynomially many, super polynomially many, or exponentially many, or super exponentially many, and factorial. Okay, so how do you make them all think about one matching? And for that, here's what we did. So I'm going to use these acronyms throughout the talk, and these are key notions that I think are very important going forward. So by MWPM, I mean minimum weight perfect matching, and by small weights, I mean polynomially bounded weights in the polynomial in N, bounded weights. So normally your weights could be exponential or whatever they are, but I want only polynomial bounded weights. Okay, and the isolation lemma says that if the edge weights are small and random, then there's a unique minimum weight perfect matching with high probability. Okay, and that unique minimum weight perfect matching is the one that all these processors will think about and find for us. That's what the isolation lemma does. And going forward, all the works from here on non-bipartite matching used these notions. And in fact, here's a small fact, a very small fact that comes from our paper, that if you have small weights and if the minimum weight perfect matching is unique, you can find it in NC. It's very easy. So now the main approach that was used for getting matching in NC was to de-randomize this isolation lemma. So if you can do this deterministically, you can find it in NC, right? So that was the main avenue. A flawed avenue, I must say. We'll see why. So in my opinion, a flawed avenue is still not clear. But what is the right decision problem? Let me introduce that before I tell you the results. So here are two decision problems. One is, does a given graph have a perfect matching? Okay. And the other is, given a graph with small weights and a target weight W, is the weight of a minimum weight perfect matching at most W? Okay. I think this is the problem to solve going forward. Any questions? Why? So this is clearly reducible. Sorry, this is reducible to this. This is harder. Okay. This is the problem to solve. And yeah, I mean, sometimes generalizations are easier to solve. People have already spent a lot of time trying to solve this by de-randomizing polynomial identity testing. And I think that's just as wrong an avenue as de-randomizing isolation lemma. So I can now state the results with respect to these acronyms. Do I repeat these, or from now on these are for us for throughout the talk? Minimum weight perfect matching and small weights. So we can reduce, for the case of small weights, search to decision. And decision is the right one. What I said was the right one. And as a corollary, we get what we wanted, the generalization of Grossman, Goldwasser-Grossman, namely like this. Oops, what did I do? Huh. Sorry? Wrong one. Okay. Okay, so proof of this corollary, very simple. Once you grant me this theorem, because the MVV algorithm for small weights finds the weight of the minimum weight perfect matching with very high probability. Okay, just the weight. It finds a minimum weight perfect matching also, but not with a very high probability. But the weight it finds with very high probability. So if you know the weight, you can use this as an oracle. And let's assume if it made no errors, we are in good shape. And we can make the high probability be 1 minus 1 over polynomial. If it made no errors, we'll get the minimum weight perfect matching. Right? So we solve the, so this is a quasi-deterministic, pseudo-deterministic RNC algorithm. Right? It uses randomization, but almost always gives you the same perfect matching, namely whenever it made no errors, and that happens with very high probability. So it almost always gives you the same perfect matching, right? Any questions? Yes, sir.
Does not choose the weights?
Yes, it does, but it gives you the weight of the, yeah, it doesn't matter which one you find. It doesn't matter which weighted matching you're looking for. The goal here was not to get a minimum weight perfect matching. The goal here was to get a perfect matching. You're right. Good question, actually. Sorry. Good question. So what did Goldwasser and Grossman do? They found a perfect matching, not a minimum weight perfect matching. I'm also going to give you a perfect matching, and I'll do it with respect to whatever weight function I choose. Right? That's up to me. Good question, though, and that will be a clear distinction going forward. Okay, so, and I just want to say that over the last 5 years, there were so many ideas. And one of the, a bunch of ideas also from this work that went into our work. This is where we gave an NC algorithm for the planar case, the first one for non-bipartite graphs. Yeah. But I will not be able to go into all these, name who all got all these ideas. It's all in the papers. No credit to be given here, other than from here we used a lot. We used the entire framework. But from the other works, we used many ideas, key ideas, all the time. So our current goal, again, so thanks to you for asking that question, because yeah, my mind is not here. I can't remember any names. Sorry. You'll see. Yeah. So We just want to find a perfect matching, not a minimum weight perfect matching. But we have an oracle for a minimum weight perfect matching. So we can keep changing the weights as we want and ask the oracle for the current weight that we are thinking about. And we'll keep changing the weights many times. But we want a perfect matching. Okay, so we are only going to solve the cardinality version, and we can initialize the weights to unit. And yeah, before I come to this, so please stop me again if you have a question, because I think I can make it clear in the hour that I have and answer a few questions also. So if you have any clarifications, I'll be happy to provide it. So here's the basic strategy. So we keep pruning edges judiciously. And by judiciously, I mean that we don't want to throw out all perfect matchings from the graph, of course, right? And keep throwing out until one perfect matching remains. That's the basic strategy. Okay, how do we make it work? So even cycles play a very key role here. So take two minimum weight perfect matchings, the green and the red, and their symmetric difference will have to have some alternating cycles. Now, and alternate edges will come from the red matching and alternate ones from the green matching. And everybody here should be able to see it in 30 seconds that the weight of the red will be equal to the weight of the green. Otherwise, if one of them is lighter, we could take that and the other edges from the other matching in the rest of the graph and get something lighter than the minimum weight contradiction. Okay. So that gives us a very, very key notion, which is the circulation of a cycle, which is the weight of even numbered edges minus odd numbered edges and absolute value, so it didn't matter where we started the numbering from. Okay, this is the circulation of a graph, of a cycle. And what I just told you is that every alternating cycle must have zero circulation, right? Let's look at, so finding alternating cycles is very hard, just about as hard as finding perfect matchings. So let's just home in on all cycles, all even cycles. So suppose that all even cycles have positive circulation. Circulation can never be negative, of course. So it's either zero or positive. Suppose all even cycles have positive circulation. Then there must be a unique perfect matching, just the contrapositive of this statement, right? And that was the old goal of all these other papers. Okay, and if you have a unique minimum weight perfect matching, you can find it at NC. That was the old goal. The new goal is to use these places where the cycle is faltering, is misbehaving because it has zero circulation, and that's where we'll find some edges to remove. Okay. And I'll just show the whole thing for bipartite graphs before going to the general graph, much easier. So here's the perfect matching polytope for bipartite graphs and the linear program for minimum weight perfect matching. So that's the polytope. XE is the variable for edge E. And for each vertex, we want xe's to add up to 1, of course, because if it were an integral solution, then it would pick exactly one edge incident at the vertex, and all edges, of course, have to be non-negative. So in fact, this polytope is the convex hull of all perfect matchings. And if we minimize this linear sum, we get minimum weight perfect matching. And now the faces of this polytope are defined by the set of inequalities, as always. The set of inequalities that are set to equality. And there are only one kind of inequality here. Very, very simple. Whether you set this edge always to 0 or not. Always to 0, then you get, you take a subset of the edges, set them always to 0, you get a face. Okay? And there's one kind of face that is very key. As I said, this is the convex hull of all all perfect matchings. And so these corner points are perfect matchings, and they are defined by setting m minus n over 2 of these inequalities to equality, and the other n over 2, which are the edges of the perfect matching, are set to 1. Right? Just to give you an example of a face. Okay, I'll come back to faces in a moment. But let me say a bit about the decision oracle. That's the decision oracle. Is the weight of the minimum weight perfect matching at most W for some target W. But once you have this decision oracle, all these problems are in NC. What is the weight of the minimum weight perfect matching? Because you can do a binary search. Weights are small. It will take only log time. Is a given edge in the minimum weight perfect matching? Very easy. Remove the edge and its two vertices. Find the weight of the minimum weight perfect matching in the remaining graph. Add the weight of the edge back. See if it is equal to the weight of the minimum weight perfect matching in the whole graph. Then this edge is in the minimum weight perfect matching. We can compute the set of allowed edges. Now, this is a very, very, very key concept. So I'm emphasizing it 3 times over. Very, very, very. So what are the allowed edges? Those that participate in minimum weight perfect matchings, in some minimum weight perfect matching or the other. Because very, very key, because the face FW, the one that has all the fractional and integral minimum weight perfect matchings, is defined by setting all the disallowed edges, the complement of the allowed edges, to 0. Okay, that's the face FW. That face contains all the fractional and integral minimum weight perfect matchings. Okay, so for all the disallowed edges, we set them to 0. We got the face. Now this, going forward again, EW will always be the set of allowed edges, those that participate in minimum weight perfect matchings. So how do we remove edges finally? So of course, given a weight function W, we only need to think about EW. Throw away all the other edges. This already has a perfect matching in it. Now, here's a beautiful fact. If you have a cycle which consists of only edges that are allowed, then its circulation has to be 0. We are in the bipartite case. Okay, we are in the bipartite case. Remember. Okay, so we have cycles are always even. We can talk about their circulation without saying even cycle. So if you have a cycle whose circulation is 0, who all of whose edges are allowed, then its circulation is 0. And I'm going to give you a very, very quick proof. So what we'll do is, suppose not. Suppose there's a cycle whose circulation is positive. Now I take X to be in the interior of this face, so that all X's are strictly between 0 and 1. And I'll rotate on this cycle, which I mean that I'll move some mass from these 3 edges to those 3 edges. So I rotate, and I rotate that way. I do 2 rotations, and one of them will give me an X prime, and I do it by only epsilon. So notice that if I do it by epsilon, I didn't jump out of the polytope, because I was started at the interior, and each vertex I did 1 subtraction and 1 addition. So the sum of the edges is still 1. So I'm still feasible, and I got an X prime that is feasible in the face and has smaller weight. Contradiction. Right? In one of the 2 options. Right? So the circulation has to be 0. Right? Okay, so how do we destroy this cycle? It's very easy. Oops, what happened? Oh, yeah. Okay, so very easy. If you have 0 circulation, then you find another weight function. And by now we only have these edges, right? EW. We throw away the rest of the edges. On EW, we impose a new weight function, completely new, which gives the positive circulation to C. And it's very easy to find that, right? Because if I put one of the edges to 1 and the rest of them to 0 of this cycle, the circulation will be positive, obviously, right? And so if the circulation is positive, this cycle will not be in the allowed edges of W prime, and we got rid of at least 1 edge, right? So we say that cycle is destroyed. And so going forward, we want to destroy many cycles at the same time, obviously, if there's any hope of doing this in NC. So we want to find many edge disjoint cycles in EW, find a weight function that makes all of these cycles have positive circulation, go to the allowed edges of of W prime, and we would have destroyed every one of the cycles. So we threw out as many edges as the number of disjoint cycles. Right? Any questions here? How do you do this in? In parallel. Good question. Can you? It's difficult, right? I cannot either. I cannot either. So I will appeal to bridge. Anybody play bridge here? There must be. You play bridge? What do you do when you have a weak hand and you need a few more tricks to make your contract? One or two more tricks only. A simple thing to do in bridge. It has a name. Nobody? Switch. That's cheating. No, legally you can do it.
Bluff?
Huh? No, bluff. In bridge. You have to apply your head, but to do that. But you can do something. No, really? Huh? No, after in playing. Here's the idea. You must have seen it before. Finesse. So we're going to do the big finesse. How are we going to finesse everything out? So we will not find cycles. The graph has enough edge disjoint cycles. We know that. Then we have this amazing fact. If you know that there are S edge disjoint cycles in the graph, if you know, you don't have to find them. If you know, then you can construct an NC this many weight functions. That's small number of weight functions with small weights, such that one of these cycles destroys all. One of these weight functions destroys all the cycles, every one of them. Okay. And these weight functions are constructed obliviously, which means that all I have to tell the weight functions is this is the first edge, this is the second edge, this is the third edge, and so on. That's all. No need to know the cycles. Okay. If you grant me this fact, I'll show you a proof if you want in a minute. But if you grant me this fact, then here's the algorithm. You try all these weight functions in parallel. Pick that function that has the smallest number of allowed edges remaining. Okay. It may not destroy all cycles, but there's one weight function that destroyed all cycles, and hence destroyed throughout S edges. So this thing will throw out S edges at least. Okay. And by this lemma, we would have thrown out at least 1 over log n fraction of the edges. So we are left with this many edges, so in polylog time we'll be done. Right? How many people want to know the proof of this? Oh, good. Because a couple of iterations of this talk ago, I gave a talk at Columbia, and they wanted a proof, and I gave the proof, and then I came back, and my host said, I got a paper out of this fact. So I think it's useful to tell you the fact. Okay, I mean the proof of the fact. So again, the fact is that if you have S edge disjoint cycles, you don't know where they are. If you know there are, then you can construct this many functions with such weights so that one of these functions destroys all these cycles. Okay, here's the proof. So let S be this a set of S cycles, and you've numbered the edges from 1 to m. And first we give very large weights, super increasing weights to the edges. So edge I gets weight 2 to the I. And then every cycle will have one very large edge that dominates the sum of the rest. Right? So the circulation of every cycle will be positive. Right? So the product of these circulations over all these cycles that we have in mind is non-zero. Now I'll show to you that there is a small number k such that z is 0 mod k. Non-zero mod k. Sorry, you're right. Yeah, please correct me, and or ask any questions if you want anytime. Yeah. So there is a small number k such that z is non-zero mod k. Let's show that. Then we'll be done. And all we need is some modular arithmetic and one small fact from number theory. So, so if Z is non-zero mod k, every cycle has non-zero circulation mod k. So we define a new weight function W prime, where W prime on this edge EI is EI mod k. So that's a small number, okay? And we'll think of it as a number, as an integer, not mod k, as an integer, okay? Now, since the circulation of this cycle is non-zero mod k, it is also, if the circulation of the cycle is non-zero mod k, it will also be non-zero with respect to these integer weights. Because if it were 0 with respect to these integer weights, it would be 0 mod k, right? It's harder to be 0 with respect to integers and easier to be 0 mod k. If it is 0 mod with respect to the integers, it will be surely 0 mod k. But we know it's not 0 mod k, so it's not 0 with respect to these small integer weights. And so each one of these cycles is destroyed by this weight function W prime. Okay? And two more lines to finish it off. So this number Z, which was the product of all these circulations, is small enough that if we take the LCM of these first Sn square numbers, it's bigger than Z. So this LCM does not divide Z, so one of these numbers doesn't divide Z, so Z is non-zero mod that number k, and we are done. Right. Questions, comments? Too easy, too hard? Too fast, too slow? Just right. Just right, right? Somebody has to say just. Uri, just right? Yeah. Okay. If you say so. If you say so. Yes. Oblivious, you just have to know the numbers of the edges. This is edge I. Okay, so now we go to general graph. So I'm done with bipartite graph. You realize that? With this, we are done with general bipartite graph. The main result is done with bipartite graphs. If you have that oracle, you can find a minimum weight perfect matching. So we go to general graph, and of course, the polytope is much harder. We throw in exponentially many more constraints for each odd set of vertices of 3 or more cardinality. We have to be sure that the cut separating S and S complement has at least one edge going out of it, because any perfect matching will match all but one of these odd number of vertices inside, okay, and must have one unmatched vertex which has to be matched outside, and that will go into the cut, at least one such edge. So every fractional matching also has to have that inequality. And now the faces are defined by setting some of these inequalities to equality, which means you have to make some of these edges be disallowed, and which means that you also have to have some tight odd sets. So as an odd set is tight if this inequality set is satisfied with equality. So that's how odd faces are. Disallowed edges and tight odd sets. And we look at this example. What's the weight of the minimum weight perfect matching here? These are the weights, zeros and ones and zeros. Perfect matching of weight 3. Yeah, but 1 is the minimum weight perfect matching. Yeah. How many do you see of weight 1? 3, good. In fact, every edge is in some minimum weight perfect matching, right? Because matchings of weight 1 are this with these two edges, this with those two edges, or this with these two edges. So every edge is in some minimum weight perfect matching. So this is EW, right? These are the allowed edges for this graph. All edges are allowed. Okay? Do you see any other problem here? Remember, in bipartite graphs, I told you that if in the allowed edges you have a cycle, it must have 0 circulation. And this red cycle has positive circulation. 1 plus 1 minus, so that's 2 minus 0. Absolute value still is 2, right? So what's happening? So general graphs don't satisfy that bipartite thing. So the obvious thing to do is apply that proof that I gave you to see what goes wrong. Why is it that it still has positive circulation, even though all these edges are allowed in this red cycle, right? For that, for running that proof, we have to find a point in the interior of the face. And there's a very nice point, because this graph is 3 regular, so all the edges set to 1/3 is a point in the interior of the face. And then we move some mass. Obviously, we'll move some mass on this fractional perfect matching. We'll move some mass from here to here, obviously, to get a smaller weight, to get to a contradiction, to get a smaller weight fractional perfect matching. And what happens if we move a little bit of mass from here to here? Look what happens. So we started with 1/3 everywhere, and suddenly these two edges are 1/3 minus epsilon. And this cut, which was exactly tight, went under tight. And so its inequality got violated. And we popped out of the polytope into a place where there's no oxygen. Okay? Terrible. Terrible things are happening. We cannot be there. So we pop right back, and we say this cycle has to be there. We cannot destroy it by throwing out edges. Right? So what can we do now? Are we stuck forever? Any ideas from the matching theorists? You have an idea?
In an odd cycle.
Sorry?
An odd cycle.
No. You have to. Your circulation is only for even cycles. Circulation, by definition, is only for even cycles. Well, what you can do is, well, you know that there is a tight odd set here. That's the reason that this cycle has positive circulation. So if there's a tight odd set, we can shrink it. And the matching theory says that this graph has a perfect matching, and no matter how we find this perfect matching, say we match this edge, then we throw away this endpoint, we can find a perfect matching in S. So we got two smaller problems. This, and once we find the matched edge, then whatever is left inside, we find a perfect matching there. Not bad, right? We got two smaller problems. That's just as good as getting a smaller problem by throwing away edges, right? So that's our strategy, okay? So in other words, whenever we have zero circulation in a cycle, we find a weight function so that we get, which defines the circulation to be not positive. Then either we lost an edge, or some tight odd set crosses C, and when we shrink S, we get a smaller graph. In either case, we got fewer edges, either by throwing away edges or by shrinking odd cycles. And we say that edge is destroyed. And now the rest of the strategy is same as bipartite. Find many edge disjoint even cycles, right? They are not guaranteed to be even in non-bipartite graphs, okay? And destroy them. Okay, so how do we destroy? So obviously here we have to find the set S that's crossing the cycle, and we prepare ourselves by finding a description of the face, which is given by the allowed edges and a laminar family of tight odd sets. Laminar because if you have crossing tight odd sets, and if you shrink both of these, it doesn't have the nice matching property anymore. Because if you shrink both of these sets, the rest of the graph may not have a perfect matching. So you can only shrink when you have a non-crossing sets. That's why we want a laminar family of tight odd sets. And in fact, the graph has infinitely many, not infinitely many, sorry, what am I saying? Exponentially many families of laminar families of tight odd sets. Exponentially many. Have you heard that word before? Exponentially many? What's the problem with exponentially many? How are these processors, parallel processors, going to find the family if there are exponentially many, right? And we are not allowed to use randomization either, right? So are we sunk? Well, we can ask for very special classes of laminar families, for instance, those that are associated with optimal duals to that LP that I gave. Even those are exponentially many. And then there's this amazing paper of Saigon Gabo and Sankowski, that says that that defined this notion of a balanced critical dual, which is unique. Not only is it unique, it can be found using primal properties, primal operations, using this oracle in NC. Sorry? Dual of the LP that I gave you, of the minimum weight perfect matching. So the dual, if it's a balanced critical optimal duals always raise duals of the tight odd sets that are laminar, or you can make them, okay? And so this is a very special class of very special dual which gives you just this laminar family. And why did this happen? Who put this fact there? I don't know. But do you? Divine intervention? Maybe, right? Because without this fact, we had no result. Les, maybe you can tell us. Evolution? Okay. I would say divine intervention here. So this is an amazing fact. I mean, really, why did this have to be there? Okay, so how do we destroy a cycle? If we have a cycle with zero circulation, we find weight function to make this circulation positive. And then we find the description of the phase, which will be the allowed edges and the laminar family. And either the cycle already lost one of its edges in going to the allowed edges of W prime, or there is a tight set S inside the laminar family which crosses C, in which case we have to shrink S, right? One problem, we have to find the set S. How do we find the set S? We have all the sets, right, in the laminar family. Which one crosses C? Do you see a big problem there? Big problem is we don't know C. We don't know any C. Remember, we applied the big finesse, which means we didn't have to know any C, right? And we thought we could get away with some hanky-panky, okay? And now we are caught here because we don't know the C, okay? And to the bridge players who, I don't know why there are none here, because normally there's always a bridge player even in smaller audiences. So if your big finesse fails, there's one thing to do, which may help you out, which is to apply a small finesse. and the small finesse in this case is to shrink all the outermost sets of L prime, which will be disjoint, and they'll get rid of all of these C's that had to be shrunk out. Okay, we'll get enough shrinking here. So if we go to EW prime and shrink all the disjoint outermost sets of L prime, we are done. We get enough reduction in the graph. And then you may ask, oh, yeah, that lemma guarantees lots of disjoint cycles. In the bipartite case, they were all even. But in the general graph case, maybe they are mostly odd. In fact, there may be only one even cycle, and the rest could be odd in the whole graph. So disjoint ones, that is. So then we turn to walks, and that's easy. So what's an even walk? It's two odd cycles with a path connecting them, and we traverse it like this. So traversing this path back and forth and traversing each of these cycles, we get an even walk, and that does everything that we wanted the even cycles to do. And so we can just find a bunch of odd cycles, connect them out with paths, apply Luby's algorithm to make sure they are edge disjoint, because we'll find a maximal independent set of these. And all of that can be done in NC. And the last thing is that if the graph is not sparse, we can do all of that. If the graph is very sparse, then it turns out that it has a lot of these triads. What are triads? These are three vertices of degree 2 next to each other, ABC. And then this is a tight odd set. And there are lots of these triads. So again, we apply Luby's algorithm to find a maximal independent set of triads, and that is enough shrinkage. So we are done, basically, right? We got this algorithm. And so until we are left with one perfect matching, we apply the big finesse, find some weight function W prime that will remove a lot of edges or shrink a lot of edges once we find the description of the face. And we apply the small finesse to do the shrinkage. And we iterate polylog times, and we are done. we're done. If you have a decision oracle, you can find a perfect matching, right? And lo and behold, this is different from the two ways of finding perfect matchings in general graphs that we knew. You know, the Edmonds algorithm and the Lovaas algorithm. And it's so different that I think it's surreal, right? Because this very, very classical problem is being solved in some kind of a modern art way. You know, you apply a big finesse, you find the face, you find a small finesse, and you do that, and you're done. And of course, there's a big question mark here, because we have to still find an algorithm for the decision problem, which doesn't use any of these algorithms. And of course, that's a big question remaining. But just to complete the story, we can also extend all this to finding a minimum weight perfect matching in NC, and we can find a maximum matching. And because this oracle is already in NC for planar graphs, because there we can count even, so we get an even simpler algorithm for planar graphs than the one that Nima and I gave last year. And then we are left with this one question of solving the decision problem. And I was quite shocked with this conclusion, I must say. Because I thought that, so I never knew how to attack the decision problem, but I always thought that the search problem will give us ideas for the decision problem. And so I was always concentrating on the search problem. And I was thinking decision is something, some side thing that will always happen. But now the decision is the main thing. How do we do it? So the good news is that the evergreen problem remains alive. Thank you. Yeah.
So you said that the approach Bipartite is not going to give you good algorithms, but it seems that what you presented is heavily relies on ideas that were raised in the FGT and the Svensson algorithm.
Yeah.
It's not clear why the conclusion about Bipartite. So
what that?
you said that early on that it's not going to help.
What's not going to help?
PIT. I mean, it's not
To PIT. How will you solve PIT from this?
You don't say you solve PIT, but you said that solving PIT is not going to help you solve the problem.
That's my belief. You may do it. I believe it.
But on the other, your ideas are based on the ideas of Rose and the PIT papers, right? Of FGT and Svensson.
They don't do PIT. They don't de-randomize PIT at all.
FGT and Svensson do.
If I give you a general polynomial identity,
Not a general. Those that you rise.
that's, I don't know, you can call it that. I don't call it that, but that's in the eyes of the beholder. Okay. Yeah, sorry. I don't agree, but you're allowed to disagree on that. It's not science anymore. Okay, you have a belief, I have a belief. So, but I don't think, I still believe that this question will give us some big tool unrelated to de-randomizing PIT or isolating lemma. Yeah, yeah. Mm-hmm. By the way, gold mine has been going on for 200 years. Yeah, the first algorithm was by Carl Jacobi, 200 years. Jacobi played with determinants, and determinants are what? Sum over perfect matchings of something. So he came up with the idea, with the question of finding a minimum weight perfect matching in a bipartite graph, and he gave a primal dual algorithm for it. Then 150 years later, Harold Kuhn gave the same algorithm, and then in 2005, Harold Kuhn found out that Jacobi has already beaten him by 150 years. So he wrote a paper that Jacobi has beaten me by 150 years. And, huh?
There's no chance before we founded it.
Actually, if Christos were here, I would ask him if the Greeks knew about perfect matching. but he's not here yet. Yeah.
I have a technical question to ask. Is it possible that maybe it's related to a main question that proving that the perfect matching is in NC will have consequences for hardness? So it would be a negative result?
Look, isolation lemma.
Like PhD.
Yeah, good question. Isolation lemma is useful algorithmically and in complexity theory. Many big results came out of that. I have no idea what will come out of this, but something nice will come out of this. I believe. Well, maybe nothing nice will come out of it, and we'll just solve the problem and be done. I don't know, but this is hard to say until it's done. Thank you. Thank you.